So why scintillators in the first place? The reason for looking into scintillators rather than the standard ion chamber, diode, diamond type detectors is that they really are water equivalent for those megavoltage photons and electrons, which means for small field dosimetry, it's a huge advantage not to be perturbing the dose distribution right there at the point where you're trying to measure it. They can be made very small. They're dose and dose rate independent for these standard beams. They're energy independent, again, for megavoltage photons and electrons. The beam quality correction factor is unity, and that really reflects that true water equivalence of these detectors. There's a very small amount of temperature dependence. It's about 0.1% per degree, so usually that's ignored for standard QA measurements at room temperature. And you can use these with the MR Linux as well. We make a slightly longer fiber so that the electrometer can be kept outside the 5 Gauss line, but there's nothing ferromagnetic in the detector in the fiber itself, and so it works quite well with the MR Linux. Our scintillators are made of an organic scintillating material that scintillates in the blue region. The detectors for the W1 are all 1 millimeter diameter and 3 millimeters long. We make 2 flavors of the W2 fiber. One is that same fiber as used for the W1, the 1 by 3 millimeter. And we also make a smaller 1 millimeter by 1 millimeter option for the W2, or of the W2 fibers. The tricky part about scintillation detectors, and the reason that although they've been used in research for a long time, it's only been with the advent of the W1 that these have been available commercially for dosimetric measurements, is that you do have to correct for the Cherenkov light that is produced within that optical transfer fiber. This is additional visible light that acts like a stem effect. The more of the fiber that's in the field, the more Cherenkov that you get. We apply a 2-channel chromatic correction based on a publication from Matthew Guyot et al. Back in 2011. And that's what really enabled this to become an easily used commercial device. You do also have to give the scintillation detector a known dose if you want your output in terms of dose. It does have a fairly stable output, but because of the damage to the plastics, you do have to recalibrate periodically as the detector accumulates dose. It's about a 2% per 1,000 gray decrease in signal. But if you recalibrate at that point, you have a slightly lower signal, but you can continue using the device for quite some time. This 2-channel chromatic correction that we use is essentially splitting the light into what we're calling the blue portion of the spectrum and the green portion of the spectrum. Our scintillator is, I guess this line, sorry, is a blue region scintillator. So most of what is captured within that blue range is scintillation signal. There is some Cherenkov that's included in that because the Cherenkov is a broad spectrum contaminant. The green portion of the signal is primarily Cherenkov, but there's a little bit of that scintillation tail that crosses over into the green region. In order to do the characterization measurements to enable this correction to be applied, we have you do 2 measurements. Really, the idea here is that you're keeping the dose to the tip of the scintillator the same, and changing only the amount of optical fiber in the field. And therefore, you're changing just this Cherenkov component. With those 2 sets of measurements, then we can take the difference in the blue channel, due only to Cherenkov, and the difference in the green channel, again, due only to that change in Cherenkov, and create a correction factor called the Cherenkov light ratio, or CLR. That CLR is then used in subsequent measurements, multiplied by the green signal and then subtracted from the blue in order to subtract the blue component of the Cherenkov from the measured signal. If you do a dose calibration, that's really just a gain factor, a unit conversion that's a multiplicative applied to this equation to change the units from measured charge into dose. So Just a couple examples. This is the smaller jig that we include automatically with the W2 to do your CLR correction measurements in your water tank. So your minimum fiber configuration would have the fiber coming straight out, maximum has it wrapping around, and this fits within a 10 by 10 field. It's not centered in the field, but really that's not critical. The point, again, as I mentioned, is not to change the dose to the tip of the fiber. The W1 comes with this calibration slab or characterization slab and has a milled out channel for that minimum fiber configuration and then for the maximum fiber configuration. This is an option with the W2 as well if you would rather have the solid slabs in addition to just the water tank jig, or you can do your measurements in the water tank. A third option with the W2 is to set it up in the water tank like you would for scanning, and use a rectangular field, something like a 2 by 20. And if you orient the field this way with the fiber, that's your maximum fiber configuration, and orient it this way, it's minimum fiber configuration. It's a little trickier because you're rotating your field and you don't have quite as much assurance that you have exactly the same dose at the center, which is why you wouldn't want to go too narrow on that rectangular field method. Or the rotation and the uncertainty and the small amount of walkout that your accelerator might have could potentially change the dose to the scintillator. The W1 was our first generation device. It has been on the market since 2014, so we're almost at our 10-year anniversary on that. It seems crazy. It doesn't feel like it was that long ago. It has, as I mentioned, that 1 by 3 millimeter active area. And because it's been out for so long and it was such a game changer when we first released it, there are quite a few publications available concerning the W1. One of my favorites is that joint publication on small field dosimetry from the AAPM and the IAEA, Technical Report Series 483, which lists the W2 KQs in a number of tables. And for every table that it shows up in, correction factors are unity for every field size. And this, again, really is a reflection of the fact that this detector is water equivalent. We're not seeing energy dependencies as that field size changes, as the sources occluded, as the scattering energy changes or anything like that. It does not require that correction for the changing energy with the change of field size in small field measurements. The disadvantages of the W1 is that this really was designed to be just a single point measurement system. We were targeting output factors with this first device in order to allow people to measure the output of these small fields. The other disadvantage or limitation is that it does require a 2-channel electrometer, such as our Supermax, in order to perform those Cherenkov subtraction calculations. So the W1 is the fiber itself and a connected shielded optics to convert that optical signal into an electrical current. It has 2 triax outputs, one for the green portion of the spectrum and one for the blue portion of the spectrum, and that's what needs the 2-channel electrometer to read in those 2 signals separately. The W2 was our second generation device then, based on what we learned with the W1 as well as feedback from users of the W1. We were able to combine the optics along with the signal processing electronics into a dedicated electrometer, which we call the Max SD for scintillation dosimetry. The fiber then is just the fiber, the W2 fibers. It doesn't have those optics on the end like the W1 does. So this has just a standard optical plug on it. So the fiber can be replaced by the user. We have then both the 1 by 1 millimeter option and the 1 by 3 available. The reason we were able to go down to the 1 by 1 with this was an advantage of combining the optics and the electronics, along with some improvements that we made to the optics, gave us a better signal to noise ratio, which then allowed us to be able to measure signal from that smaller detector. You can do your characterization measurements for the Cherenkov subtraction right with the Max SD. It has a web-based interface. You can also do point measurements directly with this device. If you're just looking at output factors or single point measurements, you can do that with the MaxSD all on its own. If you want to scan small fields with your water tank, the MaxSD will also convert each of the 10 millisecond integrations into a current output. It will perform the Cherenkov subtraction and then create a proportional current output that can be read in by your water tank electrometer. And from the point of the water tank, it really looks like a diode. It's a device that you don't apply bias to, but when it's being irradiated, there's a current that is received by the water tank electrometer. So this is what it looks like if it's set up in the tank. We have an adapter sleeve so that you can hold it in your standard chamber holder. Otherwise, the fiber is a little small for chamber holders. But this allows you to get it out away from the scanning equipment, again, to be just in water. That optical fiber then attaches to the MaxSD, and the output of the MaxSD goes into your 3D water tank or 1D water tank, I guess, scanning electrometer. So the MaxSD just acts really as a pass-through of the signal in order to do that Cherenkov subtraction. You do have to scan slowly with the device because of the timing of that subtraction happening every 10 milliseconds, as well as just the fact that it's a low signal device, and so the scans are going to be quite noisy if you scan at a rapid speed. So we recommend about 1 second measurement per dwell point. Which does add up a little bit, but remember this is small fields only. This isn't really a device that is targeting large fields. This is to get down into those tricky small fields. This is, again, images of what it looks like for minimum fiber and maximum fiber configuration should you choose to use this jig. You can also use that rectangular field method I mentioned with it set up just like this for scanning. So a couple of publications just talking about what measurement data we get with these scintillators. This was an early publication for the lifetime of the W2 anyway, when the W2 was first released, comparing the W2 with the W1. Again, we didn't expect changes just because the optical fiber is identical. The only difference on the W2 1x1 is, of course, the volume of scintillation material that's available. So this is a comparison of film and W2 measurements for a 1x1 field, 1 centimeter field profile scan in a water tank. They also investigated dose rate dependence and dose dependence, and just as with the W1, those dose rates up to the FFF beams that were tested, as well as dose linearity from 1 centigrade to 4,000 centigrade. There wasn't any dependencies seen there. Another investigation came out of the University of Alabama at Birmingham from Richard Popple's group. They were looking at Varian hyperarc treatments for very small targets and looking at agreement between W2 measurements with film for targets down to a 3 millimeter diameter target. And they got excellent agreement between the W2 measurements and the film. And actually, within the uncertainty of the film, they agreed perfectly fine, but the W2 measurements were much more repeatable than the film measurements were. I also like to show this image. This is the W2 within the chamber plug in their phantom. That water equivalence means that you're not seeing the scintillator here at the point where you would be targeting if you're doing these treatment plans. So we also include a dummy fiber with a BB at the active point of measurement so that you can see it as you're doing your imaging and your planning, and then replace it with the actual measurement fiber for the irradiations. So that's what I had for today. I know your time is precious. I appreciate you spending your time here. If you have any questions, please put them in the dialog box. I haven't seen any yet, but we'll happily stick around and answer those if there are any. Otherwise, there's more information on our website at standardimaging.com, or you can always contact us, either your sales representative or your distributor, or contact us directly through the website. We'd love to hear from you. We'd love to help you find the detectors that work best for you. There's a question about superficial or orthovoltage energies. The signal level as well is pretty low for those, as well as potential energy dependence. It hasn't been investigated. So it might be a fun research project, but no, I can't give you a definite answer on whether it's going to give you good results for superficial or orthovoltage energies. And there's a question, any tools to test gating treatment on the MR-Linac? I'm not sure what to recommend on that one. You can, I don't recall if our motion platform is MR compatible. I want to say it's not because it's been around for a little while. So testing the gating treatment, other than doing the integrated measurement with the scintillator, you would need a different motion platform. But we can certainly drill chamber plugs for your phantoms for doing that sort of treatment. A question about performing percent depth dose or TPR measurements with the PTW beam scan. Yes, you can use this with any other water tank. It really is universally compatible. The only really tricky water tank to use this with is Sun Nuclear's round tank, just because there's no inline adjustment of the positioning, and the detector is so small that getting things aligned perfectly to your small fields is just tricky with that tank. With any detector really, but particularly these really tiny ones. Question, is the detector always mounted horizontal? That's what we recommend, primarily because of the Cherenkov component. If you minimize the amount of fiber in the field, then the uncertainty on that correction is also smaller. The more Cherenkov you produce, the more you're subtracting, and the uncertainty becomes a little bit higher in that portion of the signal processing. You also have an issue with the preferential direction of in which Cherenkov is produced, and it's preferentially produced at an angle of 45 degrees to the direction of travel of the electrons that are generating that signal. And because we're relying on total internal reflection of the optical signal within that optical fiber, when you orient the detector vertically within the beam or in line with the axis of the beam, not only are you collecting more Cherenkov because you have more fiber in the field, generating more because you have more fiber in the field, you're also collecting more of what you generate because of the angle at which it's being generated. So it kind of becomes a compound problem that way. It keeps it much more simple if you always mount it horizontally in the field. A question about testing it at flash dose rates, it's under investigation right now. I know there's a publication that will soon be submitted for peer review. There is a talk at the AAPM annual meeting this year about the W2 in flash beams. So watch for that. That's kind of exciting developments here. So regarding the beam scan, yes, you would connect the Max SD to so there's a triax cable that comes with the Max SD. You would connect it with from the Max SD to the input of your beam scan electrometer. That's correct. The physical quantity that it detects, this is fluorescence that's generated in the scintillator based on the energy deposition. And so really we are measuring energy deposition via the fluorescence effect in the scintillation material. The next question, can we use it with a particle beam? It has not been evaluated in particle beams yet. There are some research publications regarding scintillators that discuss potential quenching and I think there was one other effect and I'm blanking on it now. There were a couple of potential complications, particularly or particular to particle beams. The other issue is that this is likely not going to retain its water equivalence in the particle beams. The water equivalence for megavoltage photons and electrons is very nice for the measurements that we were targeting when we were designing this, but particle beams are a little bit more tricky that way. How would you do a calibration? After you do your Cherenkov characterization measurements, so that minimum fiber configuration, maximum fiber configuration, the exact dose to the scintillator doesn't matter so much. You need a little bit of buildup because the Cherenkov effect also depends on having electronic equilibrium or changes depending on that. But after you've done those characterization measurements, you would want to do a measurement in a reference field. So for a standard linear accelerator, you would do it in your 10 by 10 field at your reference depth, give it a known dose. And our system is designed so you can put in, for these measurements, this is my known dose, and it will create that calibration factor that's then multiplied by subsequent measurements in order to convert to dose. There's a question about whether this can be used for in vivo dosimetry. We do not have regulatory clearance for in vivo measurements for this device. It's a machine QA device, not a patient QA device in terms of on-patient use. So that would be research investigation, not standard use of this. For small field scanning, do you need a reference signal? Will it improve the signal to noise ratio? You can scan with or without a reference detector. It really doesn't matter for this one because you're scanning slowly enough that the difference in one pulse here or there doesn't make a big difference. Most people actually prefer to scan without a reference signal just because it's a little simpler for this one, but you can do it either way. A question about the most accurate, least measurable dose. That's a good question. Actually, I don't have that number offhand, how low a dose you can measure. I will say that the W2 was designed so that when you measure when you scan with it and you get to the edges of the penumbra to the out of field tails, we wanted to make sure we had enough signal to be able to measure those tails accurately. Where the W1 had a slight over response just out of the field when people did kind of point by point measurement scans, and that was really because of the noise floor of the electronics. The signal was low enough that we were reaching the lower limit of what could be measured. Does the smaller size cause positional uncertainties? It can if you're not setting it up very well. I mean, depending on your system, right? So what I generally tell people to do with our water tank when they're aligning the device in the water is to align really to the tip of the fiber, because that's way easier to see than any other marker that we could put on the detector, and then step it forward in your water tank that 1.3 or 2.3 millimeters in order to get past the light tight cap and to the middle of the active portion of the scintillator. But then it's always good to do a scan of the field to ensure that you're centered properly, and use an adjustment from your water tank in order to make sure that you really are centered within your field. Excellent questions. This is great. I don't think I've had this many questions at a webinar in a while, and it's so much more fun to know people are really engaged and not just sort of half listening. Can we consider adding more fiber? I'm not sure what you mean about adding more fiber. Do you mean the scintillator itself, or do you want a longer optical fiber? Well, we're waiting for that clarification to come through. There was, oh no, there's more leads. Oh, adding additional fibers. That's what you were asking about. The system as it's designed can only handle one input at a time, so we can't do additional fibers right now. That would be an interesting way to go in the future if we could make a set that would do more than one. But right now, these are single fiber measurement devices. There's a question about any difference in measuring electrons. It certainly works for electrons. That's it's the electrons that are depositing the energy when you're measuring a photon beam anyway. But yes, it works just fine for electron beams as well. And then there's another question, is there an effect of radiation dose response changing over a period of time? Yes, it does decrease slightly over time, and that really has to do with damage to the plastics. We use a PMMA optical fiber, and I'm sure you've seen old clear plastic phantoms. They turn yellow after they've been irradiated quite a bit, and that yellowing does two things to our measurement. It preferentially filters part of the spectrum, which changes the shape of the spectrum slightly, which is why you would need to repeat your Cherenkov light ratio characterization measurements. But it also filters out some of the signal. So your total signal decreases slightly as those plastics age, as they are irradiated more and more. And so the absolute magnitude of your signal also goes down. And so that's where, if you are trying to do measurements in terms of dose, you would need to repeat both your CLR characterization measurements and your dose calibration periodically. Will it self-normalize the fade-in response as we expose it to more radiation? No, it does not. It's something that you would need to recharacterize periodically. It has no way of monitoring that at this point. I think we're nearing the end of our half hour. I will happily stick around and continue to answer questions if there are more. Otherwise, I do really appreciate your time and your engagement today. This has been wonderful. Please feel free to reach out, follow up with us if you have any additional questions. And otherwise, I look forward to seeing you on another one of our webinars sometime in the future. Thank you so much.